This study investigates the dynamics of ring linear polymer blends, particularly focusing on the topological constraints that arise when linear polymers thread through ring polymers. Such threading processes significantly affect the motion and relaxation of ring polymers, which is critical for understanding their rheological properties and behavior in materials science. Topological constraints formed by these threads are believed to be long-lived, but their direct observation and characterization, especially the dynamics of threading and dethreading, have been challenging in both experiments and simulations. To address this, the authors utilize extensive molecular dynamics simulations, alongside a novel analytical approach based on the Gauss linking integral. This method allows them to precisely identify and quantify ring linear threads without approximations, and to monitor the time-dependent behavior of these topological constraints. Their approach provides valuable insight into how the motion of linear chains influences the relaxation of ring polymers, with implications for predicting polymer blend dynamics. Overall, the work combines high-fidelity simulations and rigorous topological analysis to measure the relaxation mechanisms in complex ring linear systems, advancing fundamental understanding in polymer physics. Figure 1 shows a snapshot and schematic of threading and dethreading events between ring and linear polymers, captured via molecular dynamics simulations. Panel A presents 3 ring polymers colored red, each consisting of 200 monomers that are threaded by a single blue linear polymer chain of length 600. The visualization contrasts the initial faded configuration with the final bold configuration, where notably the rightmost ring has undergone dethreading, no longer encircled by the linear chain. Panel B illustrates this dethreading process schematically, tracing the movement of the linear chain that releases the right ring. The initial and final chain configurations are represented by dashed and solid lines respectively, with chain ends marked by circles. This figure demonstrates the fundamental mechanism by which linear chain motion leads to the relaxation of topological constraints, specifically by allowing threaded rings to become free over time. The ability to directly observe such threading and dethreading in silico confirms that these topological constraints are dynamic and governed by the motions of linear chains within the blend. Figure 2 presents the mean squared displacement, or MSD, of ring polymers with chain length 400 monomers, comparing their motion in pure melts versus in blends containing 30% ring polymers. The figure uses open symbols to show the MSD of the center of mass, referred to as G3 of T, and filled symbols to show the MSD of individual monomers, G1 of T. Black squares correspond to rings in pure melts, while colored symbols represent blends. The data demonstrate that rings in the pure melt exhibit relatively free diffusion, while those in blends show significantly retarded motion. In particular, as the length of the linear chains in the blend increases, the ring polymers become increasingly subdiffusive, meaning their movement slows and is constrained over timescales. This slow dynamics is due to the topological constraints imposed by linear chains threading the rings, effectively trapping them until the linear chains can reptate or move out of the way. Interestingly, the motion of linear chains is largely unaffected by the rings, suggesting an asymmetric interaction. The authors interpret these MSD results as clear evidence that threading strongly hinders ring motion, with the relaxation time of the rings in blends scaling with longer linear chain sizes, consistent with theoretical predictions for constraint release dynamics in polymer blends. Figure 3 quantifies the relaxation times of ring and linear polymers in blends by plotting diffusion times as a function of the linear chain length. Panel A examines systems where ring and linear polymers have equal lengths, with filled symbols representing ring diffusion times and open symbols representing linear diffusion times. The ring diffusion time sharply increases with chain length, following an approximate n to the 5.4 power scaling, consistent with theoretical models incorporating constraint release effects. In contrast, linear polymers exhibit a diffusion time scaling as n to the 3.4 power, typical of entangled linear polymers. Panel B fixes the ring polymer length and varies linear chain lengths. Here, diffusion times exhibit crossover behavior. For long linear chains, ring diffusion times scale similarly to linear chain diffusion as constrained by threading. For short linear chains, ring diffusion time converges toward unentangled ring Rouse behavior. becoming independent of linear chain size. The authors fit these data using crossover functions capturing these regimes, finding a crossover linear chain length near 80 monomers. These results confirm that ring polymer relaxation dynamics in blends are strongly influenced by the size of linear chains, with constraint release by linear chain reptation governing the timescale for ring motion. Figure 4 examines the dethreading dynamics in the ring linear blends through the correlation function CT, which measures the persistence of ring linear threads over time. Panel A shows CT for blends with ring fraction 0.3 and ring length 200, varying the linear chain length. The function exhibits a similar shape across different chain lengths but shifted relaxation timescales. Panel B rescales the time axis by t divided by a characteristic time tau 0.5, defined as the time when only half of the original threads remain. This rescaling collapses all curves nearly perfectly, indicating universal dethreading kinetics governed by this timescale. The inset reveals that tau 0.5 scales proportionally with the linear chain diffusion time tau dl, but is smaller by roughly a factor of 6, reflecting that dethreading requires only partial reptation of the linear chain through the ring. These findings suggest that the dethreading process is primarily driven by linear chain motion, and the relaxation of topological constraints occurs on a timescale closely linked to, but shorter than, the overall linear chain diffusion time. Figure 5 explores how varying the ring polymer length affects its size and diffusion time in both ring linear blends and pure ring melts. Panel A presents the radius of gyration, Rg, which characterizes the polymer coil size, plotted against ring length, Nr. In blends containing 30% or 50% rings and linear chains of length 200, Rg scales approximately linearly with ring size, indicating a dilute ring scaling regime. By contrast, pure ring melts exhibit a crossover at smaller Nr to a loopy globule regime, where Rg scales with Nr to the 2/3 power. Solid lines show fits using crossover functions capturing these regimes. Panel B shows diffusion times versus ring length. For intermediate-sized rings, Nr between 100 and 400, diffusion times in blends are an order of magnitude larger than in pure ring melts due to slow relaxation caused by ring linear threadings. For small rings, Nr less than 50, diffusion times in blends approach those in melts, since fewer threadings occur. At very large Nr, diffusion times again converge as ring-ring interactions dominate dynamics. This figure indicates that the size and topological constraints of rings strongly influence their relaxation, with blends exhibiting dramatically slowed ring diffusion relative to pure melts in the intermediate size range. Figure 6 delves deeper into the statistics and dynamics of ring linear threading by analyzing the number of linear chains threading each ring and the corresponding dethreading behavior. Panel A shows the distribution of the number of threads per ring, NT, for blends with linear chains of length 200 and ring fraction 0.3, measured from molecular dynamics simulations. Solid dots represent simulation data, while open symbols indicate a Poisson distribution fit with the same mean as the simulations. The agreement suggests that threading events are approximately independent. The inset plots the average number of threads per ring, NT, against ring size, Nr, showing a linear increase, consistent with prior studies. Panel B presents the dethreading correlation function, C of t, for the same systems. At short times, C of t curves overlap, implying that dethreading is largely driven by linear chain motion independent of ring size. At longer times, C of t decays more quickly for smaller rings than larger ones, which display a slow relaxing component that slows further with increased ring size. The authors interpret this to mean ring size affects dethreading in a complex manner, whereas linear chain diffusion exerts a dominant influence on dethreading timescales. Overall, this figure quantifies threading distribution and reveals asymmetric effects of ring and linear polymer sizes on constraint relaxation dynamics. To conclude, this work provides a comprehensive investigation of topological constraint relaxation in ring linear polymer blends through large-scale molecular dynamics simulations and rigorous topological analysis using the Gauss linking integral. The authors directly observe the threading and dethreading behavior of ring polymers caused by linear chains, which are central to understanding how these systems relax their constraints. Their results demonstrate that ring polymer motion becomes substantially hindered in blends due to long-lived threadings, with diffusion time scaling strongly with linear chain length, consistent with constraint release theories. They show that dethreading dynamics can be captured by a universal correlation function that scales with linear chain diffusion times, indicating that linear chain reptation governs the release of threading constraints. The analysis of ring size effects reveals that smaller rings tend to have fewer threadings and exhibit dynamics closer to pure ring melts, while intermediate-sized rings are strongly affected by threading. The distribution of threading numbers follows a Poisson distribution, supporting the idea of independent threading events. These findings not only deepen the fundamental understanding of polymer physics, but can guide the design of polymer materials where controlling blend dynamics and relaxation is critical. The methodology also sets a new standard for quantifying and interpreting topological constraints in complex polymer systems.